Yes, welcome to the recording. We have already started a little bit. So what I've done is I've repeated what just wrote the definition of a space that we're going to use all the time, which is a space of all matrix Lie groups, either real or complex, n times n matrices. So these are associated algebras in that they are vector spaces under plus. And scalar multiplication and that matrix multiplication is associative. So taking two matrices, multiplying is an associative operation. And we have a unit given by the identity matrix. Which satisfy that, okay, if I multiply the identity matrix, then something with the identity matrix, I get A. However, this is not a group, because even if we exclude the zero matrix, because not all matrices are invertible. And what we're going to do in the beginning is that we need a little bit of analysis, because we need to make sense of what it means. Okay, now Joachim is back in. We need to make sense of what it means for two matrices to be close and what it means for them to approach each other. So we define an inner product let's do it for the complex matrices by saying that the inner product of X matrices X and Y is the trace of X star Y. So X star here is the conjugate transposed. So meaning that if I, for example, have X being equal to 1 plus I 3, 3I, then the conjugate transposed is the result of taking the transposed and conjugating all of the elements. Like this. So this is the conjugate transposed. So this is the inner product that we want to use for the setting in entries. If X is given by matrix Xij, so these are all of the entries, and Y is equal to Yij, then okay, even though this looks technical with a multiplication and an inner product, it is in fact just taking a sum I j from 1 to n of x I j bar y I j. So it's just, in other words, just pretend that m and c is cn squared. So if you just took a normal inner product on each entry, that will be the same as this inner product here. We have these two forms because sometimes it's easier to prove things with one, and sometimes it's easier to prove things with the other form. So some of you might have not had complex vector spaces before. Some of you might only know real vector spaces. So if this is a real matrix, then of course the conjugate does nothing here, right? But for complex vector spaces, it's very then normal that it's actually just complex linear in one of the entries, and then it's conjugate linear in the other. So if you multiply a matrix with a constant, then you get a conjugate times this number. So note, so with this type of inner product, if I switch the entries, I get not the same, but the conjugate. But it's the same if we only restrict to real matrices. Also note that if I take the inner product of x with itself, then I just get the summary of all of the entries, and then x, the modulus of xi squared, and this will then be greater or equal to 0. So I'll pause the recording for a bit. Yep. So from this, I can define the norm of a matrix as the square root of x, the inner product with itself. In other words, it's just the square root of the sum of squares here. So it's just the Euclidean distance, but for matrices. And then we do the following definition. We say that lim k goes to infinity of xk is equal to a matrix X if if x minus xk, k goes to infinity, is equal to 0. So this is how we define one matrix approaching another matrix in the space of matrices. So note this is the same as saying if xk is, let's say, xk ij, and x is equal to ij like this, then the matrix converge, then each entry of this matrix k, xk, converge to the entries of x. So writing it with this norm is just a very efficient way of writing that this happens with every k, or with every entry in the matrix. So in the end, it comes down to limits of numbers. Now, why this emphasis on distances? Because we need a little bit of topology. Now, we did not require any knowledge of topology before taking this course, so I'm going to go a bit easy on this. So what does topology means? A topology are questions of what sets are called open and what sets are called closed. If you're have worked with open and closed sets in any setting, that's working with topology essentially. So definition, if I have a subset K of the matrices, for real, let's put complex here since the real is inside the complex. Then we say that K is closed if it's so that if you have a sequence inside of K and that sequence could converge to some X, then this implies that X is also in K. So something being closed means that if you have a limit, then the limit cannot escape your set. So, for example, just to have something we can draw, we can consider K as K1 as the one-dimensional complex matrix. And K2 as a collection of one-dimensional complex. So the set needs to be less than 1, and the other set can be greater or equal to less or equal to 1. So the first set will then be this set without the boundary. And the second set, K2, will be with the boundary. If I now take xk to be 1 minus 1 over k, this can escape k1, but not k2. So this is a sequence that approaches more and more the boundary. And since the boundary is not included in K1, the limit, which is 1, is outside, whereas here the limit is inside. So that's what we mean with closed. Then a subset is called open if let's say I need to make a full set. So let's say that, okay, a subset O of the matrix group. I'm going to use complex here all the time. And in the end, I'll write that it's the same for real. So is called open if the complement so all the matrices when we take out O is closed. So for example, if we do the complement of K1 above here, that will be all of the X, which is greater or equal to 1. Okay, that didn't look good, but okay. This, so it's everything outside of here. And that's closed because I can't escape because the boundary is included here, so I can't escape here. And that means that K1 is open. So this is an open set because the complement, everything that's outside the unit circle and including the unit circle is closed. There's no way for any limit to escape this set. Alternatively, set is open if for every x in O, there exists some epsilon greater than 0 such that the set ball epsilon of x, which are all y, all matrices, such that y minus x is less than epsilon. So for some epsilon, this is contained in O. So if we again go back to K1 and K2, for if I have some point x here, then I can always, with a small enough ball around it, so this, recall this was set less than 1, and this is set less or equal to 1. So I can always, with a small enough ball around it, be able to get inside of the set. Whereas if I'm here on the boundary, then any ball I draw will be both inside and outside of the set. So the set on the right is not open, and the set on the left, while the set on the left is open, because you don't have this problem with the boundary here. Now, I don't want to imply that all sets are either open or closed, because they're not. Some sets are neither open or closed, but it's true that we have this relationship that if one is open, then its complement is closed. So, and why do I are we doing this thing about open and closed? Why are we studying this? Well, it's because these words apply in the definition of matrix Lie groups, and it's basically the only thing we need to check in order to say if something is a matrix Lie group or not. So I'll pause the video again. So we'll see more examples of open and closed sets inside the matrices when we come to the definition examples of the actual matrix Lie group. So now let's turn to the main topic. So matrix Lie group. So in order to define what matrix Lie groups are, okay, yeah, sorry. Should remember to write here, remark, exactly the same for M and R. Yeah. So for matrix Lie groups, we first need to introduce the following group. So if K, bold K is either R or C, we define the general linear group G, L, and K as elements A in and the K by K matrices such that the determinant of A is different from 0. And if you remember from linear algebra, you remember that this is the same as saying that the matrix is invertible. So in other words, we are considering all matrices that are invertible, and this is a group. So hopefully you all know what a group is. So it means that the multiplication of matrices are associative. We have the the unit identity matrix has determinant different from 1, and since all matrices are invertible, we have that each element is invertible. But it's no longer a vector space. So we can't add to we have two matrices that are invertible. This does not imply that A plus B is invertible. So we can multiply them, but we sort of lose plus of these matrices. If K is a subset of G, L, and K, we say that K is open / closed if K is equal to K tilde intersected with G, L, and K, where K tilde is open / closed in the full matrix group. No, sorry, in the full matrix algebra. So something is closed inside the general linear group if it is it's the intersection if you take an open or closed set of all matrices and then just include the ones that are invertible. And then there is an exercise for this week. You can show that K is closed in GL and K if and only if you have a sequence of matrices starring K, and this is then a small k, that sequence converges to X, then X is in K, or X is not invertible. So, in other words, being closed inside the general linear group means that your limits can now escape, but they cannot escape into the group. They have to sort of become they have to then, the reason they're escaping is that it's because it's no longer invertible. So yeah, and we'll see this in a little bit. So let's do then the definition. What are the objects that we're going to discuss in this course? So matrix Lie group is a closed subgroup of GL and K. So either of the real or the complex matrices, a matrix Lie group is, I can call it G, is some subgroup that is also a closed set. So the easiest thing to understand this is to do some examples. So let's start out with a relatively simple example. We can do G equal to a constant times the identity matrix inside of GL. Let's say we can, for example, have 2R, and C is a non-zero constant. So in other words, G is equal to C0, C like this, where C is real and non-zero. This is a subgroup of GL to R. if xk, which is then some matrix on the form ck0, ck0, converge to x, then x has to also be on the form C0, 0, then either C is not 0, so x is in our group G, or C is 0, so you could have a sequence here of these types of matrices, which is 1 over n, for example, 1 over k, converged into 0. But then x would then be the matrix 0, 0, 0, so not invertible. So hence, G is a closed subset of GL2N, GL2R, sorry, and it will then qualify as a matrix loop. And so you see here that, okay, what are the things we need to check in order for things to be a matrix loop group? Well, we need to check that it's actually a subgroup. So matrices like this, if I multiply multiples of the identity, it's still a multiple of the identity. And I need to check this idea of limits. However, it turns out that most things that we would consider reasonable subgroups are actually closed. So we're only doing this checking of limits in the beginning. And then I'll show you the general example of when this fails, what we need to worry about. And then for the rest of the semester, we get into having a class of examples that we're going to use that we know fit this definition. Okay, we'll see more of these examples after the break. So now this part we're going to do some more examples. So the order I will do the example is the following. We're going to do the general linear group, then the special linear group, the orthogonal group. I'm going to do a counterexample of why we want closed, and then the Euclidean group. Then we'll see what time we have afterwards. So first, so why is GL and K a Lie group, a matrix Lie group? Well, it's closed because GL and K is, of course, the intersection of all matrices with itself. So here I could put a K here. And this is closed in itself. If I include the whole space, if I include the whole space, there's no way a limit can escape. I think I'll just disable the waiting room for the next meeting. There's no way, no way matrix limit can escape the space if you're including the whole space. And so hence GL and K is closed in itself. And it's also a group. So we didn't touch on that, but if I multiply two invertible matrices, they're still invertible by, you can either use the rule that, okay, the inverse of B is given like this, or you can use that the property that the determinant of A times B is equal to the determinant of A times the determinant of B. So if you have two things with determinant different from 0, multiply together, they still have determinant different from 0. So related to that is, so from the general linear group, you can also go to the special linear group. So these are all matrices with determinant 1. So if you think of the determinant of a matrix is roughly how they deform a volume in your space, then these are the ones that sort of preserve that volume. They keep that volume at 1. So again, if I so this is a subgroup by, again, the same rule. So if I have two things with determinant 1, multiply them together, they still have determinant 1. And they are closed. Why? If AK is in SL and K, and the determinant of AK is 1, then the determinant is continuous. So the limit K going to infinity, determinant AK, no, sorry, yeah. So then the determinant of the limit of K going to infinity AK, if that exists, so the determinant of sum A should also be equal to the limit on the outside which is equal to the limit K going to infinity of 1, which is equal to just 1. So this is closed simply because it's because it's sort of the level set of the determinant function, and the determinant function is continuous. So in general, if you have a map from M and R to, let's say, Rm, then the set, so all the level sets, so X in MR, such that f of x is equal to some c, then let's say for c fixed, the set of all matrices such that this is equal to some c, which we often write as f inverse of c, this is closed. So this is, so all level sets of function of oh yeah, and we need this to be continuous. So all level sets of functions are closed. And the proof is essentially this thing over here. So I've given you as an exercise to show that all level sets are closed, but this is essentially the proof that you can, if you have something that's in a level sets, then it will remain in the level sets after the limit. And then why is, for example, the determinant function continuous? Well, because it's a polynomial. Determinant is it's very difficult to compute. It's a very complicated formula to compute the determinant, but in the end, there's a polynomial. So it's continuous. So in conclusion, the special linear group is a matrix group because it's a subgroup and it's closed under limits. Limits can't escape it. So next example. Let's take ON. So these are all of the matrices. I'm going to take the real matrices such that A transposed is equal to the identity. So you may remember orthogonal matrices from your linear algebra course. You had that, okay, if you had an orthonormal basis, you can put that into a matrix, and you didn't call that matrix orthonormal, you call that orthogonal. And orthogonal matrices are exactly the ones that satisfy this following equation here, that A times A transposed is just the identity. So this is a subgroup. Let's check that. If A and B are in the orthogonal matrices, then AB times AB transposed. Well, when we transpose, we change the order. So that's A, B, B transposed, A. So, sorry, A transposed, which is A times the identity matrix times A transposed, which is again the identity matrix. Or we can do the, since I've done so many details, I can do the final step. Right, so meaning that if you take two orthogonal matrices and you multiply them, they remain orthogonal. So, and why are they closed? Well, take the mapping from all matrices into all matrices. which we can identify with R and square. You send A to A transposed. This is continuous. Why it's a continuous? Because it's a polynomial. The answer is almost always that it's a polynomial. Matrix multiplication is just a polynomial. Well, if I take this map, then ON is just the level set of the identity, right? It's just all of ON is just the level set of the identity here. It's all the elements that go to the identity. So it's all X in M and R, such that F of X is equal to the identity. So that's a closed set. It's a level set. So, and usually these are the way we just do this kind of thing. I mean, so you just usually you consider all matrices, then you have a defining equations, and if you just show that your limits really can't escape that defining equation, usually by showing that it's like the level set of some continuous map, then you have a closed subgroup and a least subgroup. Now let's do the counterexample. What is not a least subgroup? So I'm going to start with something that actually is a matrix subgroup, namely the collections of all matrices like this in GL to C, so all complex matrices such that each of these complex numbers have modulus or length 1. So I can write this as e to the I theta 1, 0, 0, e to the I. Okay, let's use A and B. That's nicer. To the I. No, okay, let's use theta and phi. Theta and phi, where theta is in the real numbers divided out by 2 pi set. And okay, I can even do it. We can write it as 2 pi I theta and 2 pi I phi, so that R is in the real numbers divided out by set and phi as well. So changes in whole integer does not matter for the sort of outcome. So the reason I wanted to do that is just to draw G. So we can kind of consider it as something like this, where here theta goes from 0 to 1, and here phi goes from 0 to 1. And then when we come to the edge, like we teleport here, and if we go to the edge here, we teleport here. This is a matrix V group. but it has a subgroup which is not. So let's define that one. And then I look, so I'll do the subgroup, which is then e to the I x 0, e to the I a x 0, where r is real and a is irrational. So and this is not a matrix Lie group. So why is that? Well, if I draw it as like inside this diagram here, my problem is, let's say I start at 0. I will go up here, and then I will continue here, and then continue here. But since I'm irrational, this loop I'm doing here, let's say I should continue here, sorry. And then up here, and then here, and stuff like that. So since A irrational is irrational, if I I get one long line that is dense in G. So what does it mean to be dense? It means that this line will eventually be arbitrarily close to any point in G. That is, can get in G as a limit. And the reason why is that is because, so since this is an irrational multiple of x, by just going around enough time, I can approach any combination of theta and phi that I want. So I should probably do pi here, 2 pi. And so here this so H is obviously not closed, because I can have all the elements of G as limits, but G is an invertible matrix, and so limits can escape. So why is it a problem? Well, the problem is that if I'm changing, if I'm looking at this picture here, then by going, if I need to go to this point here, then that in the in the big group, that looks rather close. But if I have to follow this line and teleport however many times, it might be a very long distance if I'm just considering inside of H itself. And that can be a problem, because it means that when we're looking at continuity and stuff like that, we have a bit of a problem when it comes to these kind of things, where the functions that are continuous are not necessarily the functions that we want to be continuous. So this group H is essentially R, but if you use the open and closed sets that come from the ambient matrix space, then points that should be very far away suddenly become very close. And this is not very good when we're dealing with this. And this is what we're kind of trying to avoid when looking at matrix groups. So I'll recording and then do our final example. So our final example is the Euclidean group. Yeah. Which is like, works like this. So you have a matrix that's on the form A0 small a1 in Mn plus 1 R, where A is an orthogonal matrix and small a is just a real number like this. You can check directly this is a subgroup and closed. So I won't go through this again, but it's again checking that the defining equations, that if you have a matrix that satisfies the defining equations, the limit can't escape it either. However, the important thing, I think, is to consider the following. So if you take two of these matrices and you multiply them, so this is the explanation of why it's called the Euclidean group. Then what you get, well, you get AB 0 plus AB, and then for the next one, you get A B plus A1. So here we see that this is a subgroup. So the end product is the same as the other one. We can, the point is we can identify it with maps. So I can write this as a TAA going from Rn to Rn. Let me just remove this subsect. So by being such that if I have a vector x, then I multiply it with ax plus b, like this. No, sorry, ax plus small a. I should probably have underlined with these to be consistent. So now if S is the same transformation, but with different matrices B, then you can check that if I first apply T and then apply S to X, so I can do something like this, then what I get is A, B, X plus A, B plus A. So this is exactly the multiplication we have here with matrices. And so I can consider this type of group of matrices as the type of transformations from R3 to R3 on the following form here. So maps on the form Tx Ax plus A are is or maps on a four or are the isometries of the Euclidean space Rn that is the maps that preserve all distances between points. So what I mean by this is that these are all of the maps such that T of X minus the difference between T of X and T of Y is equal to Ty for any X, Y in Rn. And that is why it's called the Euclidean group, because it's exactly the group of maps that makes you move around, that allows you to move around the Euclidean plane or the Euclidean space in general without changing any of the distances. So this is generated by translations, rotation, and reflections. So if you want to consider your Euclidean space with all of the maps and preserve this, you consider these maps like here. Now, why did I do this example? Well, This is because in this course, since we're using the book and the approach that we're using, we're mainly focusing on matrix Lie groups. And here we have a group of these types of maps. They work fine, but they're not written in matrix form. They're written as maps of Rn. But very often, even though it's not a matrix group like this, we can rewrite it so that it becomes a matrix group. And that was my whole point. So resume recording. Let's see. So let's do another example. Where is it? Here. Let's do SON, which is ON intersected with SL and R. So in other words, it's all matrices that are orthogonal, but with determinant 1. However, you can also actually write it as the following way. The ones where the determinant is not -1. So since the determinant is invariant under transposed, so if you transpose a matrix, you don't change the determinant. If A is in the orthogonal matrices, then I have that A transposed should be the identity. That means that if I take the determinant of that one, it should be the determinant of this one. So that means that here I have 1, here I have the determinant of A times the determinant of A transposed. And these are the same, so we get that the determinant of A squared should be 1. And so the options for a determinant in the orthogonal group is that A is either plus or minus 1. And this idea will actually be important when we come back to connectivity in the next lecture. So hence SON is only the determinant equal to 1 part. And the way you can consider it is that the SON is the rotations in Rn. Well, ON is n reflections. If you include a single reflection, you can sort of make all of the other reflections. So, so the hence the if I'm including the orthogonal matrix, all the orthogonal matrices, I'm doing all of the rotations, but I can also switch some of the orders that will make make it actually do a reflection. Whereas if I'm just looking at the ones with determinant 1, then that means I'm doing a rotation. So here I'm coming up close to the end here. So let me just yeah, let me just wrap up with important results that we'll need for next time. So theorem. So if x, y is in, say, in k, where k is a real or fake, and this is the Hilbert-Schmidt norm. Did I say that it was called the Hilbert-Schmidt norm when I introduced it? Okay, it's called the Hilbert-Schmidt norm, the norm of matrices that we introduced. Then we need the following. So we have the usual triangle inequality. Like it is an actual norm. However, we also have the following very useful property, that if we take and multiply two matrices, then at worst, it's as bad as the length of each of them. So this, yeah, and then for and then for any x in mkk, there is a sequence xk converging to x such that xk, such that each xk is diagonizable. So what did it mean to be diagonalizable? It means that if we change a basis, then it looks like a diagonal matrix. So if we, that is essentially just taking the an inverse of a matrix. So C is in GLN, L and K. Inverse of a matrix, then applying this and going back. And you think, maybe you remember that you could do this with all of your matrices in linear algebra, but in fact, you can't. However, the diagonal matrices are, you can always view your any matrix as a limit of something diagonalizable. And that means that very often, if you want to prove something, we can just prove it for diagonalizable elements. We'll do some of this next time. So unfortunately, I don't have time to do the proofs today, but they will be in the notes.